All right, part 2, VR.
All right, great, quick introduction. Okay, so my name is Suma Rosenberg. I am an assistant professor here in the Department of Computer Science and Engineering. I joined the university a little over a year ago, so I'm still somewhat new to the university. Prior to this, I was at the University of Southern California for 8 years, first as a postdoc and then as a research professor. So I have been working in the VR field now for over 15 years since I was an undergraduate student. And over the course of that time, I've worked on a lot of different projects and a lot of different things. So as a way of introducing this talk and the type of research that I do, I'd like to first just to back up a little bit and talk about the different categories of research and where my work falls into this. So I work in VR, and VR is inherently a medium that is used to achieve some sort of goal. So research in VR can span from very basic research all the way to very applied research. So this is what's called Pasteur's Quadrant, and this basically maps out how much does research consider its potential use versus how much does it contribute to what we call fundamental understanding or knowledge about the world. And so research typically falls into one of these 3 quadrants, not this one, because that's basically useless, so we'll not talk about that. So I've worked on things in VR that could be classified as basic research. Things like basically using virtual reality to study human perceptions, to study spatial cognition, how people perceive 3D space or move through it and understand it. Really as a tool and a scientific tool to study people. I've also worked on stuff that is completely on the other end of the spectrum, applied research, funded by the U.S. Army Research Lab or the Office of Naval Research, doing research in virtual reality systems to support things like training and post-traumatic rehabilitation after post-traumatic stress. And but the type of work that I'm here at the University of Minnesota, and most of the work that I've done in the past kind of falls into this middle category, what we would call use-inspired basic research. And what we mean by that is the approach that I typically take is considering how virtual reality as a medium is being used, either in video games and entertainment, in industry, or by sort of these specialized training systems for DoD or other stakeholders. Consider how it's being used. Then back up and identify what are the fundamental usability challenges that are universal to the medium that are causing these applications to suffer or holding them back, and then do research that tries to adjust those fundamental challenges. And so that's where most of the work that I'm going to talk about today would fall into that category, identifying these universal challenges to the medium and then trying to figure out ways of overcoming them. The work that I do kind of can fall across the spectrum from things that we consider to be purely immersive technologies to things that would be considered more human-computer interaction techniques, and other types of things that are not just purely computational or technological. On the technology side, I've worked on things that involve trying to create low-cost immersive displays, working on fundamental technologies for trying to create avatars, human representations of people, based on trying to capture and reconstruct them. So similar in some ways to some of the work that Gary just talked about in the last talk, but aimed at capturing people instead of objects. On the interaction technique side, I've worked on most of the bulk of my work has been in what's called locomotion or movement, because movement in 3D space is a fundamental task that is, again, universal to the medium. And then also gesture interfaces as well. How do you get the body involved in input into a virtual reality system? And then finally, some stuff that I would say classifies, kind of falls in between, that tries to link interaction techniques to, but tries to do it in sort of a system that then can support something like infinite walking in virtual reality. Now, I can't cover all of that today. That would be multiple talks. So today I'm going to really focus on three of them, kind of a broad overview with a deep dive into 1 or 2 particular techniques or experiments that we've done. Okay, so let's start off with immersive displays, because this is also a really good way to introduce sort of how the VR field has changed over the last 5-6 years. And because if we time travel back to 2012, 2013, VR was not really a thing. And is very, very different. The world has definitely changed with its respect to the prevalence of VR in the last few years. And the way that I like to talk about this and introduce sort of what happened in the VR field and the current state of it is through this model. Who has seen this before? Okay, a couple people. So this is what's called the Gartner's hype cycle for emerging technologies. And what this is a very common model that was popularized by a PR firm called Gartner. And they track sort of what happens when new disruptive technologies are introduced to the marketplace. And what it is it's a graph on this axis you have time, so as a new technology is introduced. And on the vertical axis, what you see is we could call that expectations, public visibility, or hype. Basically, what happens as far as the public's, the way the public views a new technology when it's introduced. So typically what happens is some sort of new innovation triggers a new disruptive technology to be introduced to the marketplace. At some point, the media gets wind of it, it gets popularized, people evangelize about it, and then we rise into what we call the peak of inflated expectations, where everyone is claiming that this is going to change the world, it's the greatest thing since sliced bread, your lives will never be the same. However, it's a new technology, right? People haven't yet figured out how to make it work properly and how to create applications for it if it's a new platform. So often what happens is people try it and it doesn't quite work. And many people end up rejecting the technology, saying it's a fad, it's a gimmick, it's not going to really, it doesn't really work. Some of these things might sound familiar if you're following some of the news articles that have come out about VR, in the early days of, 2014, 2015. And then what happens is you fall down into what's called the Trough of Disillusionment, where basically people are very reluctant to adopt the technology. But over time, people in research, people in industry, they work on these problems, they figure out how to make the technology better, and then you climb up the slope of enlightenment, and then eventually it does get adopted for some use cases, and we reach what's called the Plateau of Productivity, where it actually starts being used in meaningful ways. But notice that the Plateau of Productivity is not as high as the initial promises and the peak of inflated expectations. So I really like to use this model to talk about the VR field because it really describes perfectly what has happened, but not just once, but twice, because this isn't the first time that VR has come around. And so what happened in the past can actually inform the present. So what do I mean by that? The actual first time that VR came around was back in the 1980s. So actually the first virtual reality head-mounted display was constructed in the late 1960s by Ivan Sutherland, but it took until the 80s until really it became very popularized and commercialized. Some of the first prototype HMDs that resembled this were developed by NASA, but then in 1985, VPL was the first virtual reality company that was actually manufacturing head-mounted displays, data gloves, and other tracking devices, other VR peripherals. So back then, this, I believe, that head-mounted display was roughly around $15,000, and so that's 1980s money, so that's a new car price. So not within the realm of a home user, but could be purchased by research institutes or large organizations with very deep pockets. Another thing to note about that is that resolution was, I think, around like 240 by 300. So very, very primitive by today's modern graphics standards. And it was really sort of towards the late 80s that then the media got hold of it. And the first really big sort of PR blast came through the Scientific American article in 1987 written by Jim Foley, who's a professor at Georgia Tech and one of the people who literally wrote the textbook on computer graphics. And that really sort of, Scientific American, very popular magazine among hobbyists and DIY folks. And it really sort of gained public prominence after that. With Hollywood picking it up, so Lawnmower Man was one of the very popular movies that sort of envisioned head-mounted displays. It's popping up in a number of other film and TV media. And of course, then things like The Matrix, which was by the late 90s, which is like full-on brain-computer interface. So really the 90s is when we hit this big peak of inflated expectations where everyone is imagining both utopian and dystopian futures. But either way, VR is sort of being positioned as something that's like fundamentally changing the human experience of reality. But in 1995 is also sort of the mid-90s by then, is when we start to see sort of the inklings that things are maybe we're in this peak of inflated expectations. So who here has heard of the Nintendo Virtual Boy? Okay, a few hands here coming up. So Nintendo, this one is more well known. Nintendo actually tried to commercialize a VR system for video gaming. They released it. It sold extremely poorly, had very poor game support, and basically was canceled sort of after it's considered a massive commercial failure. Not many people know, however, about the Sega for their Genesis video game console also showed off a VR system at their Consumer Electronics Show in 1993, but wisely they figured out like a year later that internally that this is actually way too hard and they weren't ready, and then they shuttered the whole project before launch. And VPL, that first VR company that was producing these systems, ended up going out of business around this time as well. So VR sort of by the late 90s had fallen down into this trough of disillusionment and really stayed there for quite a long time. So I got involved in the VR field in 2003 as an undergraduate student, and at that time we were firmly down in that trough, and the reason is really can be traced to two things: cost and the field of view. So what the headset can provide and how much it costs to get there. So this is actually from about 2010, which is when I graduated with my PhD and moved to the University of Southern California. These are two head-mounted displays, which is or HMD. So if I use the term HMD, I also just mean headset VR goggles. That's the more technical term for VR goggles. So basically, you see them fall into two classes. One class of display is something that is more in the range of like a couple $1,000s, and then the other class of display, at this point, we're talking things that are in $30,000, $25,000 to $35,000 range. So what's the difference? The difference is field of view. Basically, how much of your field of vision can the VR display produce graphics that surround you? This is a map of your entire visual field. The blue shaded region is the region in which you actually see images. And this is about, that little image there is about a 60-degree diagonal field of view, which was kind of the standard by which most of the $10,000 to $15,000 headsets could do. Now this is what the head-mounted display that I used at USC, which was a $40,000 display, could do in 2010. And you can see the difference here. It's basically the difference between looking at a window that kind of peers through a world versus actually being present in that world. If you have only done low field of view VR up to that point, which is what I had only done up until 2010, and then you put on one of these wide field of view head-mounted displays, you just can never go back again. It is a completely qualitatively different experience. The problem was actually the optics. The CPU and graphics cards are still an issue. Were still an issue at that time in terms of pumping out the graphics, but more deeper than that, it's actually the optics of the displays themselves, the properties of the screen and the lenses that were being used, and how you can manufacture them. I'll talk a little bit about what changed and that made the current era of VR possible in just a moment. So if you look at what was available back then, basically you see two categories here. Things that can do above a 100-degree field of view. Again, we're talking $27,000 to $65,000 for one headset. And then we're talking about things that were in the $1,000 to $2,000 range, which is about 40-degree field of view, which is even less than that little box I showed you before. Like 40-degree field of view is terrible. Even that is more expensive than what we consider most home users would be able to use, but they're within striking distance of most enterprise businesses if they were actually useful. But I think it's really most interesting to look at this in terms of dollars per degree. It doesn't scale linearly. For every additional degree of field of view that you wanted to add into VR display, the entire system astronomically skyrocketed in cost at an exponential rate. And this is just the headset, by the way. This is not the motion tracker. The motion tracking system that's sensing your movements so they can actually update the graphics while you walk around in my lab was about another $50,000 to $100,000 on top of that. So we're talking about astronomically expensive equipment. All right, So now let's talk about what changed. What changed with smartphone screens? Now remember that back in 2008 is when the iPhone was first introduced. And before then, smartphones were flip phones. They were really small screens. They didn't really support computer graphics. They weren't big enough. And it wasn't, even the original iPhone was pretty small in its screen. It was about 2010 when my group at USC, and we weren't the only ones thinking about this, but we started to realize that, wow, the new iPhones coming out and the new Android phones that are following them, their screens are getting bigger because everyone wants this bigger phone, and they're finally getting big enough that maybe those screens could then be used in some sort of optical display system that's head-mounted. And that was not really possible before. It was back in 2010 when we actually constructed the first prototype where we basically took some optics. Now, these are expensive optics off of some old virtual reality display was sitting in our warehouse for probably collecting dust for at least the last 15 years. We slapped it in a wood frame, mounted two old iPhones in front of it with some 3D graphics in Unity, so that updated based on their internal IMUs. And then it wasn't fully head-mounted, but you could look up, you could view through it, and see what the images is like. And now there are all these problems with this prototype. So the displays were unsynchronized, they were rendered separately. It was really just a proof of concept. But we brought this to IEEE VR, which is the biggest academic conference in the VR field. And we handed it to VR experts, and we said, oh, put it on and tell us what you think. And the reactions were always very much like, oh yeah, I see you have a lot of problems to work out still, but the image and the field of view, this qualitatively looks better than this $30,000 headset that I have sitting back in my lab. So this is really like the first inclination. So to my knowledge, this is the first kind of iPhone or mobile phone-based VR prototype. And so this is really sort of the first inclination that, okay, we're on to something here. So we got to go down this road. So we came back from that, and my lab, and I was just a postdoc in the lab at this time. My mentor, Mark Bolis, was the director. And so what we did was we just started building prototype displays that basically called Franken displays. So we hired a young VR hobbyist who was about, I think, 17 years old at the time, named Palmer Lucky, who's in the LA area. And our lab was basically taking old headset frames that we acquire on eBay, buying these raw LCD display boards that were manufactured for smartphone and tablets, mounting them, cobbling together, literally holding together with tape. So we're cobbling together all these components, hence the term Franken displays. So this was a time of like early display prototyping, and but along this process, one of the realizations we had was that, well, if we're actually, all of the compute power could be on the phone, the screen, and the battery, and the graphics capability, then what is all this other stuff? The other stuff is just a housing, which could be made out of anything, and the only other thing you need is a lens to let you focus on the display. So what if we just made the housing out of foam core or cardboard? So this is the FOV to go, which we released in 2012, open source. So we had all these plans online, but we also made up 200 envelopes, and we brought them to VR conferences, and we gave them out. We had folding sessions teaching people how to fold them and put them together. This might appear to be somewhat similar to a product that was released from a major technology company a couple years later. More on that in a few minutes. So as I mentioned, we put this out in open source back in 2012. So not just the cardboard plans, but also 3D printed models for phone and tablet viewers, so you could slip a phone and tablet in. The tablet viewers are actually pretty neat because you have these big lenses. You can look through the displays, see something in VR, but you also have a touch screen. So it really was a nice casual walk-up interaction where someone could walk up, see something, use some touch screens to manipulate things and turn around and then put it down. So those were particularly interesting. And also a full-on head-mounted display that we called the Socket, which was very similar to the Oculus Rift DK1. That someone could actually, so if you had access to a 3D printer and some DIY know-how back in 2012, you could actually 3D print your own display at home. But not everyone has the DIY know-how and the access to do that, so there's only so much impact that you can have with open source. So it's about this time that Palmer decided that he really wanted to build some of these kits specifically for video games and send them around to all of his friends in his community. So Palmer, actually, his goal at the beginning was, I want to build 100 of these to present to all of my friends on Mod Retro, which was the retro gaming community that he had been involved with for a number of years. So I just want to get enough funds to build all those dev kits. Why don't I do that on Kickstarter, and then I can send them around to all of my friends in my community, and we can all kind of play VR games and kind of figure it out together. Well, history didn't quite turn out that way. As some of you may be aware, Oculus did not just make 100 of these. Oculus ended up raising on Kickstarter, breaking some records, over $2 million. And so that really set in motion quite a much larger effort than Palmer had originally envisioned. But really what changed was a couple years later when Facebook came around, and to the surprise of everyone in the VR field, including the folks at Oculus, acquired them for $2 billion. Actually, we know today that actually what Facebook paid, including everything else that is closer to 3. So this was significant in that it was a landmark event in the VR field. The first time a major technology company had invested this level of resources in VR. But it was also significant because it kicked off a technological arms race with the other major technology companies, Microsoft and Google, and et cetera, where now everyone is trying to invest in VR because we're not going to let Facebook run away and own this new medium. So this really is the inflection point at which everything in the VR field really changed. And also later that year is when Google released Google Cardboard, which, as you might note, looks very similar to the FOV to Go. So design similarities aside, what Google did that we could not do at USC as academics is provide the software ecosystem on Android, to provide the developer support, to provide all of the tools for software developers and content creators. So Google, I have to give them credit for creating the mobile ecosystem surrounding the cardboard that really kicked off smartphone-based VR. So fast forward now a few years, and basically this is some figures I was able to find from 2017, so a couple years old now. But 2017, it was estimated that the global installed user base for VR devices, including smartphone-based VR, so all VR devices, had reached about 28 million. And they were shipping hundreds of thousands of headsets every quarter, and this has only continued every quarter since then. So where are we now? Clearly something has changed, and we're on an upwards trajectory. Now, I would say we're probably not all the way up this slope of enlightenment to this plateau of productivity, but I think the evidence is pointing to the fact that we've at least somewhat climbed out of the trough, and maybe we're like halfway up the slope of enlightenment. That's if you're being optimistic. Now, what if I want to be a pessimist? If I want to be a pessimist, I'd look back at history and say, well, this isn't the first time VR has come around, and if you look at some of the news articles that have come out about VR, there is some indication that some people are saying, oh, it makes people motion sick. Oh, it's a fad. It'll never be really widespread use. It's a niche technology. And I understand some of these concerns, but again, I think some of that is could be symptomatic of not the fact that VR is actually not working. It's the fact that the hype and the way that the media has sort of portrayed what VR is, the state of VR now, is somewhat over-exaggerated where it is, and now so we're a little bit, that reaction is somewhat in just the result of the fact that people's expectations had been inflated because they don't remember VR back in the 90s, so it all seems like this new fantastic thing. So if you can't tell, I'm not really a pessimist or an optimist. I'd probably call myself somewhere of a realist in that I acknowledge both of these two narratives to be sort of reflective of what's going on. But I wouldn't be a researcher who has spent the last decade and a half working in VR if I didn't believe that VR was going to be a very important and play a very important role in a variety of applications in our society. So why, if we have so many VR headsets then, if it's so popular, then why hasn't it just been embraced uniformly? And I would say one of the reasons for that, the narratives that I like to convey, is that VR is not just a headset. A headset is just a piece of technology that you wear in your head. And what VR is a medium, and a medium is a method of communicating something. It's a gateway to an experience. And what we have now are headsets that work, but the medium itself as a storytelling medium or as the design of 3D applications is still pretty much in its early stages, just like the early stages of film were very primitive by today's modern standards of cinematic storytelling. And so to think that just because we now have good headsets, that suddenly now VR is just going to work magically 100% of the time, is to ignore this fundamental fact that the headset is just one key component, and VR is much more than that. So with that, I'd like to now shift into some more of my more recent research topics, and that really sort of tries to get at this other part of VR, which is sort of like, what's the user experience, what's the usability challenges, and how can we overcome those? And one of the ones that's going to really motivate a lot of this is one that if you've ever tried VR, how many of you, by the way, have tried VR? Okay. How many of you have experienced motion sickness as a result of trying VR? Okay. So still a fair amount of you, not everyone, which is pretty consistent with sort of observations. Not everyone experiences motion sickness. It's a lot of variability among people. But if you look at some of the headlines, and these are some of the ones that I've snipped out of the popular press during sort of like the introduction of consumer VR into the marketplace, this is something that's considered to be probably the biggest concern among virtual reality developers, startups, and even the major technology companies that are trying to create applications for VR. By the way, my favorite one is vomit reality. I just love that headline. I think it's really clever. So why is this such an issue? What's causing it? Well, there are a lot of, as I mentioned, there's a lot of variability between people. We don't even have a common description of like what actually cyber sickness, what we call it, is. Could be nausea, disorientation, some eye strain, things like that. Everyone experiences it differently. But we do know that there are some common causes or things that can often induce these sorts of symptoms. One of them is due to how we achieve movement, which in the VR field we call locomotion. And if we look at some of the early applications when the Oculus Rift DK1 first came out, most of the applications were aiming to give you experiences like this with a seated use. So basically, you sit down, you put on a headset, and then they say, oh, we know how people move around in 3D environments. We do this in video games on your PC or your Xbox or your PlayStation all the time. Hand them a controller, you sit down, you press forward on the joystick, and it flies you forward. That's how games work. Well, it turns out that locomotion in VR works a bit differently than on viewing something through a desktop. And the reason for that is because in VR, you're actually experiencing you're getting the visual input that's telling you that you're moving. However, what's happening is liquid swirling around in your inner ear relative to gravity, what's called your vestibular system, is giving your sense of balance and motion, is telling you you're staying still. And when those two senses are basically giving you different information, if that conflict becomes too great, the resulting phenomena that you experience is motion sickness. So fundamental big observation that they figured out was, okay, having people fly with these game controllers while seated, that is a recipe for many people to make them sick, so that's not a great solution. Okay, so now let's talk about my research in locomotion and specifically aimed towards how we can do better types of locomotion that will hopefully avoid some of these issues and have other benefits as well. All right, So one thing that we thought about was, well, if you have a very small space and the only thing you can do is like sit or stand in one place and fly around using a controller, what can we do? Is there a way that we can make that better and less nauseating? And what we came up with was a technique called field of view throttling, also now commonly known as tunneling. And so we actually patented this filed it back in 2014. It was granted a couple years ago. So what happens is basically you have your whole field of view visible, and what we do is we artificially tunnel down the field of view, basically mask it out using, just call it in black, in the periphery as you're moving. And then when you stop moving, basically the tunnel vision goes away and kind of tunnels back out. So you kind of view this like looking through a paper towel tube. Let me give you a view of this. This is actually a study that was not done by us. This was our Fernandez and Feiner at Columbia, who actually did a scientific study that showed that this measurably reduces discomfort from motion sickness. So you can see they tried to do this in a very subtle way. So you can see it's kind of tunneling in as you move very slowly, and then as you stand still, the tunnel vision effect kind of gradually expands outward, because when you're standing still, you're not getting all this motion information. So you can see there's no reason to restrict your field of view. In fact, you probably want to be able to see things and look around. So you don't want it to interfere. But when you're moving and flying forward, we're limiting the amount of visual input that's getting to your system that could cause motion sickness. And as I said, in their study that they did a couple years ago, they found actually that it measurably, in a controlled study, reduced motion sickness. So this has pretty much become the de facto standard technique that's in a lot of commercial VR applications to reduce motion sickness. So if you've done any VR applications, this is one's called Google Earth VR. It's called comfort mode, dynamic vignetting, tunneling. It's often buried in the menus of major VR applications, but under one of those monikers, you can usually find it, toggle it on, and then set how much you want. Okay, so great. We have at least one technique that we can use to make people less motion sick, but it doesn't eliminate it entirely, at least not in all people. And so it's not a perfect solution. It's just a mitigator that can be used sometimes. And so it's good that it exists, but it's not a 100% solution to the problem. So Valve came around. Valve is the major software company in but also the creators of Steam. So they manage sort of the PC ecosystem for digital distribution of video games. And they've also been working on VR for a long time. And so they came around and they introduced the Lighthouse Tracking system, which was then commercialized into the HTC Vive VR system. So this came around like a year or two later. And what basically that introduces the idea of doing room scale VR. So the idea here is you have two emitters, those little at the either corner of those cube up top, that are basically mounted within some sort of open room scale space, and then those are actually tracking your positional movements within that space. So as long as you stay within that volume, you can actually move around physically, so instead of flying around with a controller. So great, we have the ability to move around with our bodies. If our body motion matches what our visual motion is, then there's a one-to-one correspondence, and our perceptual system won't complain by causing us to get motion sick. So very well known that people in the VR field use room scale VR because it's a much more comfortable experience. Also, it's more natural. Also, you don't have to think about moving. There's no explicit control. People intuitively know how to move around in the real world, so it also increases realism. It requires less attention, less cognitive burden on users. There's all these reasons and benefits why walking around in VR is much better and it's the gold standard. However, one might notice that there's an inherent limitation with this, and the way I like to introduce that is just by looking at what I call the YouTube, the VR blooper videos that started showing up after the HTC Vive was introduced. They're pretty indicative of this. This is one of the favorite ones I found on YouTube. Yeah. All right, so it should be pretty obvious what's going on here, right? You're going through some virtual environment that was not designed for your physical space. You want to go through a large environment. You want to go through virtual cities. You want to be able to go through these fantastical worlds. But your physical space is a room of limited size. And at some point, you are going to, if you're physically walking, you are going to hit a wall, or at least that's the worst case scenario, or you're going to walk outside the boundaries of what can be motion tracked. So what does this mean? Does this mean that all VR experiences are forever going to be limited to the size of one single room? Because it seems like the laws of physics are at odds with what we want to be able to do in VR. So that sort of now is the conceit that introduces sort of the major themes of research in my lab nowadays. I named my lab the illusioneering lab, which comes from a combination of illusion and engineering. And the idea here is we're going to use some perceptual illusions in the VR system to sort of leverage knowledge about human perception and try to overcome these fundamental engineering or problems, the physical space problem in VR specifically. The first sort of technique that we can point to that sort of kicked off this line of research was not done by me. This was back in 2001 by researchers at UNC Chapel Hill, and it's called redirected walking. Has anyone heard of the term redirected walking before? Okay, we have 1 or 2 people. Okay, so redirected walking is basically a technique that gets you to walk along a different virtual path than you're in the real world, and does it in a way that's imperceptible, meaning your brain doesn't know what's going on. So in their original paper, they set up this zigzag sort of environment. It was like a fire drill type scenario. They walked between all of these different X's on the blue path here, so following the zigzag path in the virtual world. That's what they perceived that they were doing. But in the real world, they were basically walking back and forth between the two same physical points within a small room-sized space. So how did they do that? So there's a few different techniques that we can use that go into what we call redirection. The first one is rotation gain. And the idea here is that, excuse me, we're going to upscale or downscale some component of the user's motion. In this technique, what we're going to do is going to manipulate the rotation, what they physically do versus what is displayed in the headset. So in this example, they're going to rotate 90 degrees in virtual space, but that's going to get mapped to a 180-degree turn in the physical space. So they feel that they're going, if we do this in the right way, they feel that they're going around a turn in virtual space, but they're just going back over the space they've already gone in the real world. The key here is that you don't just rotate something around the user while they're sitting still. They have to move, and you take that movement as input and you scale some component. So they move, you scale it up and down as a multiplication factor. We can also do this with other components of the user's motion. So what if we do translation, forward movements? The easy way to think about this is scaling your step size so you can go through a greater or compressed distance in the real world versus the virtual world. So you might walk at a slower speed in the physical space, but travel greater distances or even compressed distances in the virtual world. And then the other one, which is a little more complicated, is what's called curvature gain. The idea here is that we do what's called a corrective gain, where we get the user to unconsciously alter their movements. And the way this works is, as a function of your forward velocity, you're walking forward, we slowly rotate the virtual scene around your head position, very slowly. And what this basically does is you will unconsciously sort of correct for that slight rotation and walk along an arced path. So the idea here is basically taking a straight path and bending it into a circular arc. Typically, redirected walking systems will often apply these 3 different techniques as sort of like primitive techniques that you can either apply in combination, or at set stages in the virtual world, you go around a turn, you have some rotation gain, then we kind of like then have a stage where you're doing rotation curvature gain doing an arc. So you might do these separately, sequentially, depending on what they're doing, or have some sort of intelligent system that's actually applying them dynamically all at the same time. So here's an example of actually a live VR system that uses it. So this was a light field rendering VR gallery that we did for SIGGRAPH for the AR/VR conference, was won first place in 2015. And so basically this was a gallery of stop motion animation, image-based rendering content that was created with the School of Cinematic Arts at USC. But when we entered this into the contest, they said, okay, bring it on stage and do a live demo. And we were like, we have all this big space. What are we going to do? Our gallery won't fit, as we've designed it, within the space that you have. So what we did was we ended up introducing this redirected walking. And because it's a linear scripted experience, there's a narrator that's walking you through the gallery. We could plan it out in such a way that we could use redirected walking and then do it in a much more confined space that we could demo at SIGGRAPH. So you can see here, we put in, so the virtual path is still here in blue. The teal square here, a rectangle, is the dimensions of the physical space, which is also marked in yellow tape. We put that couch there for no other purpose than to just give you a sense of scale that this is basically, that this whole thing was being experienced within a space that you could actually have like in front of a couch in a living room. So let's talk about perception for a minute. Why does this work? The fundamental phenomena that's being employed here is what's known as visual dominance, which means if you are getting conflicting information from your visual system, and remember I told you about the visual vestibular system before, liquid swirling around in your inner ear, motion relative to gravity, it turns out when those two senses are in conflict, vision will, will tend to dominate over vestibular. Turns out vision is very powerful. It will also dominate over audio as well, other senses. Excuse me, I'm getting over a cold. So. Now, we know already that huge conflicts cause motion sickness. So we don't want to do that, right? But if we can do this with a slight conflict that can't be perceived and doesn't cause motion sickness, then maybe we can exploit that visual dominance to be able to walk through bigger spaces, bigger virtual environments, and smaller physical spaces. And that's basically the key to making redirected walking work. So the first question is, how do we actually measure how much people can detect or perceive? And the way that we actually do this is do what's called a psychophysical experiment. So Frank Steineck from University of Hamburg is credited with really doing the most extensive studies that have actually measured how much redirection can you do. And the way they basically do this is what's called a two-alternative force choice task. So basically, they're given a stimulus. For example, they're asked to rotate, and you rotate them more or less in the virtual world. And then you ask them, were you rotating faster or slower in the virtual world versus the physical world? Or you could phrase the question differently, but it's always phrased as a yes-no. And that's why you call it a forced choice. They are forced to choose. They don't have the option of saying, I don't know, or they're the same. And you basically do this for a whole bunch of different gain, what we call gain levels. So everything from really, really noticeable and slower to identical, all the way up to really, really noticeable and faster. And if you do this with like enough people and enough trials, you need hundreds and hundreds of trials over the whole experiment, you can actually then just pool them all together and then compute the probability for each gain level that people could detect it. So that's what you see here, this graph. So this is the probability of responding, like yes, and this is like the probability of responding no. So what we know here is that if you have a 50% probability there, we call that the point of subjective equality. Basically, that's flipping a coin. So instead of asking people, are they the same, we just know that if you're randomly getting 50%, that's randomly guessing, that's subjective equality. So that we're basically, instead of asking people explicitly, we're letting the data tell us at what point are these basically the same. We should expect that they're going to be the same around a rotation gain of 1, basically meaning the same rotation in the virtual and physical world. What we actually want to find is the periods where they can reliably detect that these illusions are happening. So we look at the 25% and 75% probabilities. By convention in psychophysics, they consider that to be 75% probability of being able to basically, which is basically saying you are if 50% is where it's subjectively equal and it's random, then halfway between that and a sure thing is what we would consider to be a reliable detection threshold. And so that's how they came up with those numbers, these numbers. And so basically, all of these studies that were going on during like the early 2000s were basically producing these numbers. So we know that, for example, for rotation gains, you can amplify rotations by 49%, dampen them by 20%, And if you, as long as you keep it beneath that level of manipulation, people can't perceive it. Okay, so that is sort of an introduction to redirected walking. Now I'm going to talk more about my specific ongoing research in this area. So when I got involved with doing redirected walking research, it was probably around 2008, 2009. And during this time, some of these perceptual studies were still being done. They're being sort of validated. So we kind of were getting a sense at that time of how much redirection we could apply before it becomes perceptible. And the answer is a fair amount. There are definitely limits, but you have a good amount of sort of perceptual real estate here to play with to redirect people. But I was also interested in asking other questions. One question is, how much redirection can we apply before it becomes noticeable? Now, this is different than the answer of whether it's perceivable. The answer of whether it's perceivable is asking the question, is your brain capable of telling the difference? The question of whether or not you notice that it's happening is also a question of like what you're doing. Are you engaged in another task? Are you distracted? What are you looking at? How fast are you moving? So the answer to that question is we can apply even more redirection if we probably do things that design VR applications that engage users, distract them, and things like that. So those perception thresholds are really conservative in that we're really talking about like just are you capable at all, is your body capable of being able to tell the difference between those visual and motions and your vestibular sensation. But even beyond that, I was interested in asking what I would argue are potentially more interesting or more important questions, but also harder to measure questions. I wanted to ask questions that were about more centered around how does redirection actually impact the user experience? How does it impact your knowledge of 3D space? How does it impact your behavior? How does it impact your ability to perform a task? Because if we're actually suggesting that these techniques should be used in VR applications, then we should probably understand what the effects are going to be. Yes?
Question on regarding the noticeable limits, was the research on those limits, was that done in like a black and white checkered room, so there's like no external stimulus and they can tell well, or is it like what kind of environment was that for?
Typically, those are trying to performed in either a sort of like just like a standard like sort of empty or reasonably empty room, or sometimes some of them have been done in just like an empty virtual outdoor environment with like maybe they'll have some trees and a horizon line and stuff like that. So not super cluttered, but just sort of like a standard reasonably sparse but game environment that has some things in it. And then often, if you can see outside the edges of the display, try to block that out with some sort of like blocker so you don't get anything coming in from the real world to pollute that experience. Did that answer your question? Yeah. Okay. Feel free, by the way, to raise your hand at any point, and happy to answer questions in line. Okay. And then finally, so that was the thing that the theme about how does redirection impact the user experience is something that's really central to my work. And then the other thing that's sort of central to my work is, all right, how do we, if we take these techniques out of perceptual theory and want to use them in practice, how do we actually design and implement systems and algorithms that can actually use these in a more intelligent way rather than just having to manually plan a scripted experience? How do we actually engineer systems that utilize these techniques in effective ways? So I'm going to touch on, for the remainder of the talk, I'll focus first on the user experience question, and then I'll go into more of the computational engineering work. I want to talk about specifically a couple other illusions that I've looked at over the last few years. So first is what's called change blindness illusions. So in order to introduce the concept of change blindness, which is very well known, if you've ever taken an undergrad psychology class, you might have seen change blindness as a phenomenon be introduced. So it's been known for many, many years to be sort of an interesting thing, but it's never been applied to this VR walking problem before. So let me give you an example of what I mean by change blindness. Everyone take a look at this visual scene right here. I'm going to change something, and if you've never seen me give a talk before, you can play this game. If any of you have ever seen me give a talk before, don't cheat because I've shown this example in other talks. Okay. Anyone see what's changed? Go ahead and shout it out. Okay. What was that? Any guesses? Okay, we have a base of the tree. Any other guesses? All right, let me make it real easy for you. Whoops. So I was pretty confident you won't get it. I've given this talk many times to probably hundreds of people now, and no one has ever actually gotten it. So why was this so difficult? This is difficult because I flashed that interstimulus image, that black screen, for just a split second in between it, and that disrupts the motion in your visual field. And that, turns out, is how humans perceive changes in visual in 3D space, or in any sort of visual space, is they get motion, and that's how they update their internal representation of the scene. So by disrupting that for even a split second, I made that very, very difficult. So let's talk about how this interesting property of our brains can now be leveraged in VR to also address this problem. So here's the sort of like a little animated walkthrough of the proof of concept experimental environment that I mocked up in order to test this illusion. So the basic idea here is that they walk down a hallway, a door opens, they enter a room, they're going to walk to I gave them a task which was just walk up to turn on a computer, and then what happens is behind their back, the door changes and the structure of the environment changes. So what happens is that door, let me do that again, you can see swapped 90 degrees along that wall, and then the entire hallway moved along the different side of the space. So they're walking along basically the perimeter of the space, and then they continue down the hallway, they walk to that next room, and basically this process can continue infinitely. Here's the actual live VR system to prove we actually built it. So you can see they're going through. This is a very large warehouse-sized space, but the actual test environment here was only about 15 by 15 feet. But the entire virtual environment was a gigantic office building, about 3,600 square feet, that they could explore with a dozen offices spread throughout it. So this entire illusion in this experiment was happening to them 12 times, one time in each office, over and over and over again. So clearly, people walking through this are going to, experience something where they're going to know that the room that they're in is small, but this office building is ginormous. All right, so first thing I did was I tried to ask in this experiment. I ran this with 77 people in 2 separate studies. First thing I tried to do was just ask them in as many ways in questionnaires and other types of ways. Did they figure out, did they notice this illusion happening? And so one of the first thing I found was like, wow, it really works. Only one person out of 77 people, and we were really trying to tease out and ask them leading questions about this illusion. Only one person actually identified that the doors had moved. So what does this tell us? This tells us 2 things. One, there's always some weirdo who's going to ruin your perfect record no matter what you do in life. And then the second thing is that this is an extremely, extremely powerful illusion. I was expecting to have to run statistics on this, to have to be able to sort of like discern, okay, some people notice, some people not. I was not expecting it, with the exception of one person, to work 100% of the time on everyone. So this, I came back to this. I actually had to run the second experiment as a follow-up just to confirm that this wasn't like a fluke. So this illusion really, really is powerful. One of the things I did in the second experiment was I tried to ask them a series of what we call embedded questions, where I basically gave them a bunch of questions that asked them different things that could have happened in the environment that were weird, and I embedded them within a list of other things that could have happened in the environment that were weird, that were decoy questions that didn't actually happen. So, for example, this might be hard for some of you to see. I felt like I was getting bigger or smaller. I saw the virtual world rotating. I saw the virtual world get brighter or dimmer. This is the one that we actually care about. Something in the virtual world had moved. I saw the virtual world flicker. And then felt like I was being moved around. And then I tossed in this last one here, felt like I was being turned around, as sort of like a general feeling of like, I feel like I am turned around, meaning I'm not, it might be a level of like disorientation, or like I don't know really sort of what's going on spatially. And then I asked them to just rate for each one on a scale of 1 to 6, how much they felt that the sensation, or noticed that that happened. And what I found is, first, the decoy question, the question we care about, something in the virtual world had moved, was rated about the same as all the decoy questions, so extremely low. And not everyone always puts 0 for everything, so that's why it's always a little bit. But you can see if you look at all the decoy questions, it's basically like, pretty strong evidence that no one was really feeling that something had moved. But the sense of I feel like I was being turned around kind of makes sense, that they entered into a physical room that they could see. It's not it's bigger. It's not a tiny room, but it's still a fairly small room compared to the gigantic virtual environment that they were walking through. So it makes sense that they would kind of get the general sense of, well, I don't know how that happened, but I was probably being turned around. And that was actually, when I talked to people and sort of got like qualitative feedback, many people would say, yeah, I had the sense that like I was walking through this bigger virtual space and there's no way it should have been able to be possible, but I have no idea how you did it. Actually, many people tried to suggest that maybe I was using something like redirected walking, where I was like rotating them around, which I was not doing in that experiment. So they're trying to come up with explanations that actually to explain it, but they never came up on the change blindness one. But again, I also want to ask these questions that are somewhat more difficult and harder to ask. I wanted to ask how this actually, see how this actually affected their perception of the 3D structure of the space. So one of the things I did was have them draw sketch maps. So this was actually the environment. So there were some right angle turns. You can see it's kind of like this big square with 3 offices per hallway. And I asked them to sketch maps of the environment that they just created, or just went through, and then I handed those maps off to a bunch of independent graders, and then basically just asked them, given this image of an environment and given these maps that people drew, how much does this sketch represent the environment in the picture? And so those people just rated those blindly. Didn't know why they were doing it. It was just recruited for the purposes of providing quantitative values on these sketches. Turns out those sketches ratings were all very high, so I won't show you any like bars or statistics. What I will do actually is just show you the pictures. So overwhelmingly, they look like this, right? So, and it was confirmed through those grader analysis that like these pictures were strongly representing the structure that we wanted them to achieve. And if you think about this, right, there's no actual way to represent this environment on a single map, because every single time you enter an office, the whole structure of the environment is dynamically changing. It's a violation of the laws of physics. So this provides sort of evidence that when these illusions exist and you don't perceive them, your brain figures out a way to resolve any sort of conflicts and put this together into an environment that makes sense. This indicates that these illusions are really practical, potentially, in these types of environments, because people will still be able to learn the structure of the environment and know where they are. So another cool thing that we can do with this technique, because it has discrete changes rather than continuous changes, is we can do what's called passive haptic feedback. We can actually align physical objects to it. So what you're seeing here is they're walking down a long road, and you can see they just entered onto that road and walking down here, and they're stepping onto this big gravel pathway, which is so I had the bright idea, why don't we truck about 1,000 pounds of gravel into the lab, which was not the smartest thing I've ever done. We were cleaning up after it for about several years after that. So when I moved to the University of Minnesota, my job talk, I promised all the other faculty here I would not be trucking 1,000 pounds of gravel into the building. But what it did get us was this 10-meter long, so like 30-foot long roadway, where every time you step on it, you get the crunch under your feet. You really get that sensation. And you could tell when people stepped onto it, the moment that you give any sort of physical sensation or physical feedback in virtual reality, people react. Like it ups the ante dramatically because it becomes more real. So you get that sensation of that illusion, and then you exit out, you enter into this building, and I paused it because I wanted to get to this part, explain this before we get to it. So they're going to walk to the edge. This was funded by the Army, so this was a search task, searching through for a stash of hidden weapons. So they're going to walk here and watch what happens when you look into those crates. There's basically a double whammy of change blindness illusions. They entered in let me go here. They entered into the hallway, that inner room here, and that doorway moves from here to there, so it swaps 90 degrees. And then they had entered into the building at this end of the road. That moves all the way back over there. And so they exit out through the building that they came in through, kind of walking straight, coming at it diagonal, and then ending up at the other end of that walkway. So essentially when they walk out of that room, that building, they now step back onto the walkway, continue the direction they are going, and then can walk to the next building, and then reusing that gravel walkway, basically turning a 10-meter long physical road walking surface into an infinitely long walking surface, as long as they are visiting the buildings. That is one thing that you have to do in these types of techniques, because if obviously they just continued walking straight, they would not be able to do it. But with the right types of experiences that support these sort of like interactions, you want to search through things and you want to experience like these types of structure, you can do some pretty amazing things that actually also aligns, kind of breaks the physical world, virtual world, but then aligns it to the real world, which I think is sort of a really cool, interesting thing to do. Okay, any questions about change blindness illusions before I move on? Yep.
What happens if the user in this scenario walks into the wall? Like, would their camera stop at the wall, or?
In this particular implementation, I did not introduce any collision detection that prevents them from walking through it. One could do that. I've done that in some experiments in the past where I've simply tried to like make them like they could slide along the wall and not go through it. The reason I don't usually have to do that is because unless someone is explicitly trying to break your system, no one really walks through walls in VR. It's just something that people generally don't do unless they're trying to be brats. So, yes.
Do the people in your users, do they know what the physical space they're in looks like?
In this one, this one was done as a demonstration, so most of the time, yes, they do know what the physical space looks like. There are some experiments that have been done in the past where people have actually blindfolded them before they walk them into the room. I did not do that in my experiments.
Does that affect the way that they perceive their sensation of the turn?
I certainly think it would be, because if you don't know the dimensions of the physical space that you're in, if you're blindfolded and led into a room, you probably have no idea how small it is, so you'd probably be able to not get that sensation as much. So, yes.
Have you done this with any like users who have been trained to be hyper aware of their environment, like military?
That is a fantastic question. I have not done that in the context of a formal scientific study because getting access to those populations has been difficult. However, I can tell you that when people in this demo have noticed, I have demoed this to 3-star generals. I have demoed this to the former, to General Petraeus, who came to visit the lab, and he had no idea, right? So these, however, occasionally someone pops up that does. I did have one person who did notice, not in a study, but in a demonstration, turns out that they were a firefighter. And the firefighters are very, very attuned to structure of 3D spaces because it's a life and death situation. Other ones that have been pointed out to me are, what about architects? They think about 3D space in ways that probably most people don't. I think that those people would be probably more primed and more sensitive to these types of illusions if they are done in an obvious way. But the other interesting thing is, I'm not sure it matters, because this doesn't really seem to cause anyone any discomfort. If anything, they think it's cool because it's kind of magical. It's kind of like something that they can't experience in the real world. So even when those people have noticed, they have then said to me, that was really neat. So it might not even matter if people notice. Okay.
So going around in circles, sometimes people have issues focusing on things. So don't you see that happen?
I mean,
have their gaze on something?
I think with the spaces that you're walking around in with these types of things generally are sort of large enough, and it's done in such subtle ways that you are not like spinning around in a small area. So I haven't noticed any sort of disorientation or things like that occurring from doing that. What I did have, well, you notice this cable here is very long, and what I did have with people walking in circles was the cable wrapping up and tangling. So at one point during my career, I actually made a study environment that implemented this as a figure 8 so they could untangle their cables themselves, and it was done for no other reason than to make my life easier. Okay. All right, let's move on to the next illusion. All right, for the next one, I like to credit my my inspirations when they come up. So the first one was inspired by techniques in psychology. The next one is credited by science fiction. So who here is familiar with the BBC television show Doctor Who? Okay, great. Most of you. For those of you who are not familiar, it's a sci-fi show where an alien by the name, called the Doctor flies through time and space through a time machine called the TARDIS. It's basically this size. And the idea here is that when you open up the door to that, it's actually quite large. It's actually, according to the lore, infinitely large on the inside. But from the outside, you can walk around it. It's a very small kind of phone booth-sized object. And there's always on the show this sort of like trope when he brings companions in and they walk inside and they go, it's bigger on the inside. And it always seems so magical to me, that idea. And I wanted to experience what that magical illusion felt like. And then one day I realized, you know what? You're a researcher in VR. You can do that. So this next illusion is what I call the big impossible spaces, but we can also think of it as the bigger on the inside illusion. All right, so here's how the experiment environment that I mocked up to test it. Again, this is kind of modeled as like a generic office building type environment. So in one, this is basically 2 rooms. They walk into a room. They walk to a desk to turn on a computer just to give them a target place to walk to. Then they walk outside the room, walk down a hallway, and then halfway down the hallway, the first room is removed and the second room is added. And so basically what this means is, and then they walk to another computer and then turn it on. So they end at the right location. So this basically means that this environment with 2 rooms is bigger on the inside because we're essentially squishing them together. We can view this as either shortening the hallway to squish 2 rooms on top of one another, or we can view it as essentially squishing the walls or moving them to intrude on each other's spaces. But in either case, we are creating this sort of 2-room environment where it's bigger on the inside. And we also have a nice quantitative way of measuring how impossible it is. Like I call this like the impossibility measure. And that's the square footage overlap between the 2 spaces. So the amount of overlap between the 2 rooms is basically by moving those walls in so they overlap one another. I can then calculate the percentage. And so like 25% overlap, 50% overlap, I now can actually say, by manipulating just that variable, I can then say how much impossibility can I introduce into this environment before people begin to perceive it. So of course that's the first thing I did. I used the same sort of 2 alternative force choice tasks that I introduced back when we were talking about measuring redirected walking thresholds. So basically, is this an impossible or a possible space? This is one where when people came into the environment, I actually very explicitly explained to them what impossible spaces were. We used pictures. They actually went through one. So they knew what impossible spaces were, and they're really trying to determine whether these spaces are possible or impossible. And again, I do this with a whole bunch of different levels of overlap between the 2 rooms, do this with a whole bunch of trials. They do this over and over, do this with a whole bunch of people, and eventually you pull all those probabilities, and then you let the data tell you what people could perceive. So here we have overlap of room area, 0%, that means 2 side-by-side rooms, perfectly possible, 15%, 30, 45, all the way up to 75%, which is basically almost entirely overlapping one another. And then the vertical axis is the probability that they responded that it's an impossible space. So that 50%, this 0.5 here, 50%, that is essentially flipping a coin, random chance. And so what we looked at here is basically what's the point at which it's random chance? When are they randomly guessing? When can they not tell? And what we found is it was about 56% overlap between the rooms. So think about that for a moment. If you know that you are a virtual reality designer and you are creating environments that involve indoor environments that have rooms, typically rooms that are adjacent to one another, and you know that each one you can make overlap 56%, the one adjacent to it, and people won't be able to tell, you've immediately dramatically increased your virtual real estate without having to do anything really that complex. You just make each room when you walk into it much bigger than it could be. So this is a technique that's readily just deployable in so many VR applications. And the other thing to note would be that people were really trying to break this illusion and trying to figure it out. So these numbers are probably conservative. What I mean by that is I noticed during this experiment, people were doing this. Trying to like walk to the wall and measure using their feet, does this distance actually make sense? The other strategy I noticed that people were doing was they would stand in the doorway so they could see the hallway and the wall, and they would go like this with their head to try and back and forth to try and see. So if someone's not actively trying to answer this question, really trying to tell, I suspect you could do even more than that, and then people wouldn't even notice. But again, I wanted to also see how will people behave. How does this impact your ability to perform tasks? Not just do you notice or not. And for this, I mocked up a distance estimation task. So this is a technique called blind walking, which is often used in VR to measure distance perception. And the idea here is when they get to that second room, they're asked to look towards the wall, imagine where they were physically standing when they were at that first desk and turned on that first computer. Then the display goes dark, so they're completely blind. And then they are asked to walk until they are physically standing on the spot that they were standing when they turned on that first computer. Now, the caveat here is that in an impossible space, that location might be just a couple steps away. In the 75% condition, I think it was only they had to walk 2 steps and they'd stopped, and that's where they were actually standing the first time. Would they actually stop to where they were physically standing, be accurate, or would they mentally separate the 2 rooms in their minds and then walk an exaggerated distance as if those 2 rooms were possible? And so this is sort of guidelines that just demonstrate what we would expect to happen with either hypothesis. So again, overlap level in the rooms. This is the walk distance as a percentage of what it actually physically was. So 100% means they're totally accurate to where they were supposed to be. So I told them to walk to where they were physically standing, and they did it every time. So we'd expect it to just be 100% flat line. And this is just mathematically what it works out to if they're, with every level of overlap, if they are mentally separating for the 2 rooms and walking these exaggerated distances, turning impossible environments into possible ones in their head, we would expect them to follow that red horizontal guideline. And this is what I found in all the data in the experiment, what people did in 2 different conditions of how we were implementing this. And I think it's pretty clear which of those 2 hypotheses are true. I don't really have to provide you with statistical evidence. It's pretty obvious that, that they were separating these two rooms and acting as though they were possible. And the cool thing is, I think this is one of the coolest results I've ever done in experiments. The cool thing is because 75%, they were at like 90% probability of telling me in that task, I'm in an impossible space. They knew they were in an impossible space because they were actually responding, yes, it's impossible in that task. And yet, even though they knew it, they were still walking those exaggerated distances to where, because that's what they felt that they should be doing, even though they were told to walk to where they were physically standing. So I think this just reinforces this idea that even if people notice, it might not matter because they're behaving and acting as though the physical world rules still apply. Here's just a little quick sort of twist on this illusion. I call it a twist because it's actually what's called, it's playing with that same idea, but it's implementing it as what I call a twisty hallway illusion. So basically, what happens here is all the rooms here are pre-modeled and the hallways are not. And what happens is every time that they exit a room, a twisty hallway is procedurally generated by the Unity game engine. So we implement this in Unity. They walk to the next room, and you'll have to forgive the programmer art here. This was done by a computer science student. But the basic idea here is like this is modeled like a museum type application where there's like an exhibits and things that you want to walk around it. You choose a door, you walk out, the twisty hallway is generated based on where you're standing in the space and how much space you have, and then it loops back in. The old room, by the time you get to the end of the twisty hallway, is deleted, and then there's a new hallway added. So we call this flexible spaces because all of this stuff is sort of like procedurally generated by an algorithm on the fly. And again, turns out this approach, it works. People in this one, people do actually comment that the twisty hallways do make them feel kind of like, oh yeah, I'm getting a little turned around, but I'm not getting motion sick because I'm just following the hallway, so it doesn't matter. So this wouldn't be appropriate for something like a tactical 3D shooter game or something where the 3D space is something you need to learn and matters. But what about educational applications like a museum where you really just want to get to the content that you want to experience? It doesn't matter what the hallway dimensions are. What you want to do is get to the next piece of content because that's something that is of interest to you, and this technique would allow you to do that without getting motion sick because you don't have to, because you can actually walk around. So we think that this has some interesting implications, this technique, within the context specifically of things that are like educational applications or video games that are like maybe puzzle-based or story-based that don't really have a strong coherence to having a physical environment. So in summary, for this, we have a new class of spatial manipulation techniques that extended this definition of redirected walking. We had this very limited definition of just these motion illusions. And now we have these new class of things that can also manipulate the architecture, the geometry of the virtual world. And this has actually been implemented within at least one or two commercial VR applications. For those of you who have access to a VR system, there's an experience called Unseen Diplomacy that uses these impossible spaces illusion that you can get on Steam VR. All right, so we're at 11:10, so I've been talking for a long time. Is it okay if I go a little bit longer? Okay. All right, so I just want to briefly touch on some of the algorithmic work, which is sort of like the redirected walking systems. So the techniques that I showed you before were really based on interaction techniques. Now, what I'm going to show you now is basically algorithms that can deploy redirected walking. And we're going to go back to those redirected walking techniques that were really grounded in those motion illusions. So those rotation gains, those translation gains, and those curvature gains. So for these ones, we're really talking about the virtual world is fixed, static. We're not employing any change blindness illusions. We're just manipulating your motion within those models. As a quick reminder, this was sort of the application that I showed you, the demo where that we created for SIGGRAPH that used redirected walking to explore this gallery. And I was all like, isn't this great? But if you now wanted to nail me on something, like what's the limitation of this? It's that it's a scripted experience. It's that it's linear. There's a narrator that walks you through it, and you have to go through those gallery points in a set order to make it work in the way that we want. And if you decide to go off script and not follow our plan, you're going to go off the track, and then the redirection is going to break. It's not going to work anymore. So that's the limitation of that technique. It really works in that specific scenario, but can we do things that are more generalized? First of all, what happens if someone tries to do that? People don't always do what you tell them. What happens if they are going off the script and they are about to hit a wall? In this case, what we do is we're redirecting people. They get to the edge of the physical space. What do we do? Turns out there's a way we can do something we can do. It's called a reset or a reorientation event. And the idea here is when you're about to have an imminent collision with an object, you can actually employ an intervention in the virtual world that gets them to turn around. You can employ a distractor. You can give them an explicit instruction. You can build something into the environment that they need to interact with that causes them to have to turn. Then you employ rotation gains as they turn to whatever it is that you're causing them to walk towards or need to focus on. And that rotation gain points them away from the wall, so they're walking now pointed towards the center of the space, and then they can continue walking without hitting the wall. So that's kind of how we handle these failure cases when we try to avoid them as much as possible, but with redirected walking, we have to do something imminent. We employ these reorientation events. This is an example of one that we built into a narrative for a virtual scouting task, again for the US Army. You can see it's popping up a panoramic photo. They had to scout an environment, so if they were about to hit a wall, we popped up a prompt that said, you need to take a panoramic photo because you're scouting the environment. And then so they rotate around, they fill the little panorama on their smartphone, and oh, by the way, by the time they're done with their panoramic photo, now we've redirected you, and now you can keep walking. So it's kind of a way to build it. This is just a demonstration of like a technique, a way you build that into a narrative of an existing environment. Okay, so I'll skip over this slide just in the interest of time. So basically, the way that you can use redirected walking in a real system is that you have to start with the question, how much freedom does the user have? How much can we predict them? There's three basic classes of VR experiences and the way that we're going to implement redirected walking is going to be different for each one. The first one is what happens if you have a linear route, right? If you don't have any turns, if you know that they're just following some predetermined path or a hallway that doesn't have any branches, you can use what's called static planning approaches. Instead of having to do this by hand, can we create algorithms that do this more intelligently? We have branching pathways, so many environments have some level of predictability but are not completely open. For example, walking through any sort of interior building environment has hallways that branch out but has structure that allows you to predict where the user is going to go. There are dynamic planning approaches that we can use for that. And then basically the last one is open world. So completely sparse open world. At any point you can turn in any direction and walk infinitely. That's our worst case scenario, in that we can use only what's called reactive algorithms or greedy approaches. I've done work in all three areas. I'll give you a quick taste of algorithms that address each of these three scenarios, and then we'll close out the talk. So the first is, let's start with reactive algorithms, which are basically open world. You have no predictability, so what do you do? The basic idea here is, the existing approach was, well, what if we just steer the center user towards the center of the space, which basically means wherever they are, we just calculate where the center of the space is, and we just apply redirected walking gains to curve you and get you pointing towards the center of the space. And that's all we can do because we can't do anything smarter than that. The other one is algorithm that was previously suggested, steer to orbit, which we do the same thing, except we just calculate a path along an orbit around the center of the space to get you to walk inside of a circle. Both of these algorithms are okay. They're not great, but they really break down in a physical space that's not perfectly square and open. So for example, if I wanted to use redirected walking in my lab, my home, my space, I might have open spaces, but it's not perfect. There might be some furniture off on the side, and there might be quite a good amount of real estate that I have to redirect people, but it's not clear that there's a perfect center to it. There's obstacles and there's things like that, and there might be dynamic obstacles, people. These algorithms basically break down, or at worst case, they'll steer, if something is an obstacle kind of like in the way between where it's trying to steer you to, it will literally steer you into it. So it'll actually do the exact wrong thing in that case. So one of my PhD students, Gerald Thomas, basically had the observation that this kind of motion planning in physical spaces was there are techniques that are being solved in the field of coordinated robotics. And we can actually, if we reconceptualize users of VR systems as robots, admittedly, probably really bad robots, but if we think of them in that way, we can actually start applying some of these techniques that have been studied in robotics in new and interesting ways. And that's what led to the development of P2R, or called push-pull reactive algorithm. So this was just published earlier this year at IEEE VR. So the basic idea is, given a physical environment which contains obstacles, we can generate what's called an artificial potential function. And what that basically is that is an abstract function that represents the different configurations of the system. And basically, the function itself is like a surface that describes the energy state of different configurations, in this case where the user is in space. So by doing that, and I won't get into the math of it, this is just showing kind of like the intuitive idea of like how the function works. Basically, we can calculate a gradient field that represents where in physical space, depending on where they are in physical space, what's the most advantageous place for that person to be in terms of avoiding physical obstacles, collisions with the physical environment. Then we can then apply redirected walking algorithms with that gradient field as an input, and just apply like gradient descent to push you towards every frame as you're walking through the environment. We use redirected walking to just push you and nudge you towards a more advantageous configuration of the system. So the basic idea here is basically without getting into the stats, we compared this to steer to center, which is the previous state of the art. Basically the number of resets that had to occur during a walkthrough, there's a number of those reorientation events. We want to use those as less as possible, so lower is better. And basically what we found is our algorithm performs statistically significantly better when obstacles are present, both objects are located around the boundaries and objects in the interior. Basically, takeaway here is P2R is the new reactive algorithm state of the art because it performs significantly better than the previous algorithms in terms of its effectiveness in redirecting the user and avoiding obstacles. Next, quick touch on dynamic planning approaches. So the basic idea here is that we have sort of branching hallways and things like that, environments that have some structure, but there's still choice. The idea here is, okay, if we're going through an environment, let's just like conceptualize of what a user might do. So if they're going down this hallway, they might go forward, they might go turn left or right, they might go backwards, turn around, go backwards, turn left or right. This kind of looking like a graph-like structure to me. So what if we try to represent this as a graph? So that's exactly what we do. Based on the this is the virtual environment that they're navigating. We generate a prediction graph, which essentially allows us to then input into an algorithm and says, this is a graph that represents the likely directions the user is going to go. Now select your redirected walking gains more appropriately, because now you can know what the user is going to do, and then you can bend those paths to make them conform within a given physical space. So if there are these reactive algorithms that have very low deployment overhead, they basically are so greedy and easy that you can just apply them anywhere, but they don't perform as well because they don't have predictive capability. If we have a prediction graph, we can use predictive algorithms. There are a couple in the literature that I didn't introduce, but basically the idea here is we can use them if we have this prediction graph. The problem was everyone was always creating these prediction graphs manually, so they are tedious, they have more overhead in deployment, and they don't work for dynamic environments, because when the environment changes, now the graph is no longer valid. So the basic idea was, given that these approaches exist, if we come up with a way to dynamically generate prediction graphs, we can bring that down and use these all in a completely automated system. And that's essentially what we did. We basically used what's called navigation meshes, which are often used in game AI to plan how agents move through spaces. We essentially applied those to generate a graph. So you basically grow out polygons in 2D space on like a floor plan of an environment where you can walk and where you can't. You analyze the connectivity of those polygons, and then you kind of smooth it out and then form like this kind of graph. So you can do this. You don't need a person to drop and create a graph manually. Basically, you can now algorithmically, given a virtual environment, generate these graphs on the fly, making it entirely automated. And this is just a basic idea. We did this at back in 2016. One of my PhD students published this paper. Just as a short paper, this is a demonstration of this working live in the system, these dynamic prediction graph generation, which and then again enables those redirected walking algorithms without any sort of manual intervention. And then finally, the last thing, and then I'll close out, is static planning approaches. And the basic idea here is we're walking through some sort of linear route to the environment. Now, we have a pre-scripted experience, or maybe a segment of an environment with no branching hallways. Basically, can we do better than just what we were doing before, which is random, like hand crafting and then making just decisions of like, well, I think maybe if I rotate them by 50% more this direction, I can get them pointing back. Let's try it, and then we basically just do this through trial and error. What if we actually have a system that can do this and find the optimal solution? So that's what we basically did. We wanted to try and find like what is the most optimal set of gains that we could do. And so the basic idea here is if you apply combinatorial optimization, what you'll look at is this example here. You're you're facing in this direction. You're walking, and you're gonna take a 90-degree left turn and walk forward. Depending if the system knows you're going to do that, they could apply curvature, rotation, and translation gains that will end up in any of these possible configurations based on the gains that we choose. So basically, by selecting these gains, you basically have this branching tree that says this is where the user will end up when we apply them on their next action. Problem is, there's so many gains that the branch factor in this tree is 27. So basically, you iterate forward in this, it becomes very computationally intractable. You have a combinatorial explosion, and basically, you can't compute anymore. So basically, one of the contributions of and I won't get into the math of it, one of the contributions of my former PhD student who's now graduated, Mahdi Asmandian, he was able to find a way to intelligently sort of discretize the space and manage this combinatorial explosion in a way that allows us to actually compute the optimal solution. And then I'll skip that in the interest of time. So basically what we end up here is, here's like a given walkthrough. So you basically, this was a large virtual building. and this was the physical space. And so basically any path that we draw, this was just one that he randomly did for a walkthrough, input that into the algorithm system, and then basically it optimally conforms that to fit within a much smaller physical space. And we know it's the optimal solution because we've exhaustively computed every single possible application of gains for the entire walkthrough, and then we just pick the one that has the fewest number of resets. This is an example of how when we deployed that within an actual live system. So this is a real estate application. A real estate company in Los Angeles had provided us a building, which is a model of one of their real estate properties, and wanted to do virtual walkthroughs of it. And so so we planned them like a virtual walkthrough where they had to follow a specific path through the environment, but they were able to do this without a single reset. They were able to go through this massive warehouse, use redirected walking, and never encounter a reset, and we didn't have to plan that manually. The algorithm just did it for us. So this gives you just a quick example of how much of an performance improvement you get when you can optimize this. This is basically the virtual distance between the resets. The longer you can walk before we have to deploy one of those resets, that interventions to get you pointing away from a collision. So longer is better. This is in meters. And this is the size of the tracked space along the horizontal axis. Sorry, I was pointing with my mouse. This is the size of the tracked space. So bigger tracked spaces allow you to do better redirection. So basically, how big of a space do you need to get? This is basically no redirection. So basically, every time you are walking the length of a tracked space, you are hitting a reset. This is a reactive, the old steer to center algorithm. This is a dynamic planning algorithm, one of those dynamic ones. And this is the combinatorial optimization algorithm. Cool thing here is notice what happens when you get above 10 meters, which is this is the size of a tracking space in many large-scale VR warehouses, like the one I had at USC. You basically then reach a point where you can infinitely redirect without ever hitting a wall. Because at some point, if you can compute the optimal solution and you have a path and you have a big enough space, you don't need to reset anymore. You just walk infinitely forever and the illusion just holds. So that was a really cool finding, that when you can actually find the optimal solution, then you could potentially never have to reset and you can just walk forever. Now 10 meters might sound large to you, but I would point to the fact that one of the things that's been really exciting over the last year or two is that we're getting these new kind of portable VR systems like the Oculus Quest that are completely untethered. They don't require wires to PCs. They don't require tracking. They do all the tracking on board. So now you can take one of these inside-out tracking headsets, go out to a gymnasium, a parking lot, a field, a big open space, and now these sort of redirected walking techniques can really shine there, right? Because now we're not tethered to just a small space that's hooked up to a graphics-capable PC. VR is going, it's kind of the next paradigm shift, I like to say, in VR, is going towards building-scale VR, not just room-scale VR. And the hardware is beginning to move towards that trend. So to wrap up, the virtual laws of physics are malleable. Turns out that we don't need to physically strictly conform to the real world laws of physics. And human perception is similarly malleable. Turns out that humans will very quickly adapt and recalibrate as long as we don't do things that are that basically break the assumptions of human perception. This means that VR can not only recreate real-world experiences, but they can actually transcend real-world experiences. You can experience things that are bigger on the inside. You can experience change blindness illusions. You can experience things that are impossible to create. And so in that way, I like to say that virtual reality is the only real way we'll truly get to experience magic in our lifetime. And that's one of the things that really excites me about being a VR researcher. Some of the algorithms that I've mentioned, specifically the rotation and curvature translation gain techniques, are actually built into our open source toolkit, which is integrated with Unity and is available on GitHub and free for non-commercial or commercial use. So if you go to my website, you can Google Redirected Walking Toolkit. You can download that and find it. If you're interested in experiencing redirected walking, one interesting one to point to is The Void, which is a virtual reality theme park attraction that exists in probably, I think it's maybe 15 cities now across the country, including the Mall of America. And they have been using redirected walking within their experiences for quite a time. Probably the most popular, well-known early use of redirected walking that they popularized amongst game developers. All right. just a couple quick shouts to current research directions that I'm currently pursuing. Everyone I always get a question is, you did it for one person, what about multiple users? The answer is yes, you can use redirected walking for multiple users, but it also introduces collisions between them because they are now all in different places in the virtual world and physical world. So it's an interesting computational problem. That's an ongoing area of work that's currently in research land. This idea of being able to walk within cluttered spaces, this is just like a quick example of some of the work that my students have recently done to try and do redirected walking and planning in dynamic environments. So in this one, in the overhead view, the red box there is that cart, and they're pushing the cart, and then in the background, it's triggering when the visual environment changes, and then we replan a new route throughout the environment. So new algorithms that can now apply these types of techniques in dynamically changing physical environments is definitely an area of interest. And with that, I don't need to really address that. I would just like to quickly acknowledge all the PhD students that worked on this work and engineers and collaborators at the University of Southern California. And then my current research group, the Illusioneering Lab here at the University of Minnesota. And it's always important to acknowledge who gave you the money to do cool stuff. Army Research Lab, National Science Foundation, Office of Naval Research, USC, and Google. And then last slide I promise, is that we recently obtained 100 Oculus Quest systems that are available across the college. They are at CSE IT and can be checked out by any student in the college. I'm currently using 60 of them in my 5619 VR class, but the remaining 40 are available for everyone. So please, I encourage you, if you're interested in VR, go check out a headset and do some tutorials, and you try the redirected walking toolkit if you like. It's a resource that's available for everyone here now. So I was really excited that the college decided to invest in that. And with that, I'm happy to stick around for some more questions. I know it's 11:30.
So is there redirected walking in the Oculus Quest?
The Oculus Quest is just a platform, and then there's some games available for it. To try redirected walking, you'd have to download the toolkit and try it in Unity yourself.
Because I'm interested in, in a Google Street View, you'll jump into some street somewhere and then start walking. Is that?
I mean, I would love to do that. I would love to convince Google to actually let us do that within Street View. I'm not aware of a way to do it now.